Okay, so hello students, good evening. How are you? So we are back with our series of fluid mechanics, lecture number 6. Okay, so firstly, tell me the screen is visible to you and I'm audible to you. Okay, okay, got it. Got it. Thank you so much for crazy gamers that are students from GNV Baleri, GNV Karimnagar, I think, and Semi Reddy. Okay. So I welcome you all in this lecture and thanks for the joining because usually at this time we are taking tea and enjoy the view of evening, but here we are studying physics, so which differentiate us from the other rest of the other, and it's a good thing to not to be like others. It's a good thing. Okay. So finally, we are on our lecture 6. Before that, we have covered the Bernoulli's equation of continuity, streamline flow, turbulent flow. We have discussed all the things. Okay. In today's lecture, we are going to see some application of Bernoulli's equation, okay, like Venturi meter, flux velocity, and Torricelli's law. Okay, this is also in your syllabus. So let's just get started with it. What do you guys say? Ready? So, equation of continuity and Bernoulli principle is the heading of this section. And we have covered it. Now, in this, we have only restricted to application of Bernoulli's principle and Venturi meter, dynamic lift, Torricelli's law. So this is what we are going to cover today. Okay. Before that, I want to give you a quick review that of Bernoulli's equation so that you will not trouble in the lecture during the lecture. No? So Bernoulli's is the equation of conservation of energy. Of energy. So there are two conservation in physics. First of all, the conservation of energy, okay, and the conservation of mass. So each and every physicist that have proved some laws, present some equation that basically tells us that we are conserving the mass, conserving the charge, later on you will study, and conservation of energy. If you talk about Bernoulli's equation, it is the representation of conservation of energy. If you talk about the continuity equation, continuity equation, it is the representation of equation of conservation of mass. So somehow we are discussing the same two ideas, that is conservation of energy, either it is mechanical, and conservation of mass. There is another conservation which is conservation of charge. Okay. The charge will be discussed with you in your 12th. So we left it for now. Now we only focus on the conservation of mass and conservation of energy. That is the only two conservation that we are dealing with. Bernoulli's equation say that, hello Shiva, how are you? I'm glad you have joined. Okay. Now, I like you, like everyone that have joined. I think this crazy gamer, the student from JNV Valeria has joined first time, na? So, like, why we are here? Firstly, let me talk about this. Why we are here? Why we are giving so much time? And at that time, at the 5 to 6, that usually a time to take rest, because all the offices, all the worker that working in your nearby area, you will see that at 5 o'clock in the PM, they will get, yeah, okay, 9 to 5 is the job. I always heard about it. Why we are taking some extra effort? We are extending our time to 5 to 6, 1 hour more we are discussing. Why we are doing this? Because we want something extraordinary. So for that, we have to make some extra effort now. You want to go to you want to crack G means, or you want to crack NEET examination. Okay, these are not easy examination. Okay, so for that, if they are not easy, you have to push yourself. Okay, so in that case, this 5 to 6 is not a time that you will assume ki, yeah, nah, why I'm extending this time. This why should be clear to you, firstly, each and every one of you. If your why is clear, then your how will automatically be clear. Like if I lock you in a room, okay, and I will not give you any kind of food and water for up to 7 days, then I unlock the room, then what do you eager to find? What is your first choice? Is it the video game that you are hoping uh, you want from your parent? Is it that Apple mobile phone or MacBook? What do you want then? Tell me. Students from JNV Baleri and Semi Reddy, JNV Ramnagara student Shiva. What do you want then? Tell me. Think about it and then tell me. If I lock you in a room for 7 days without food and water, and when I unlock that room, what is your first priority? Yeah, I understand you want to kill me. That the who's the one that have locked me without food and water. This is the first priority of yours, but at that time, I guarantee you that is not your priority. You want to have something to eat, something to drink, food and water. Very good for JNV, Karimganj. Very good. Food and water is the first priority. Okay, JNV Ramnagar is saying that to crack IIT and NEET. Okay, so after having no food and water for 7 days, the first aim that you will acquire is how to crack JEE at IIT. Okay, so this is the fun part, guys. The correct answer is food and water. Okay, health is wealth. Very good. So food and water. Do you know and do you need any kind of strategy to find that food or water? Or specifically, you are agreeing with water. You very badly need water. Do you need any kind of strategy? Air is present in that room. I'm not saying that I am sucking all the air of that room also. Okay, there is no vacuum, so you will not survive in the vacuum for 7 days. You do not need any strategy to find the water. You will go search and everywhere. Where's the water? And wherever you will get the tap, you just open it and bring the water. Because your why is clear. Your why. This why. Kyun? This is clear to you. If why is clear, then how? Kaise? I'm able to get that water is automatically clear to me. So same goes for your preparation. No? If your why is clear, why you are preparing for JME, why you are preparing for NEET, why you are spending your time in the preparation of that particular examination, what does it mean to you? Then your how will be automatically clear. Then you will not there kind of thought will not came in your mind that why I should attend this class. This is at 5 to 6. Oh, I'm feeling bored. No, I'm not attending this. These kind of laziness thoughts will not come to your mind when your why and how is clear. Okay. So now let's focus back on this uh, conservation of mass and conservation of energy. Okay, thank you so much, guys, for the clapping, for the cheering up. Thank you so much. I'm glad. Okay. So now guys, let's back to the work. Now get back to the work. Okay. So continuity equation, we will say that it is A1 V1 equals to A2 V2. A1, let's say this is the tube that we have and water is flowing through that. Area of this side is A1, area of this side is A2. Water entering here with the velocity V1, leaving here with the velocity V2. So we can say that velocity multiply by time, multiply with area of cross section is always constant. This is the equation of continuity, which means the rate of flow of water, the rate of flow of mass, the mass which is entering per second, leaving that from the same time. Okay. Whatever the mass enters, mass of water, same mass will leave. Or you can say the volume flow rate. Got it? Now, Bernoulli equation says that E1 plus, or we can say that delta P plus mg delta H plus, sorry, rho g delta H plus 1 by 2 times rho delta V square is equals to constant, which means change in pressure energy, change in potential energy. This is potential energy, also termed as potential head. And this is kinetic energy, also termed as kinetic head. So if there is a question come in JEE mains and it talk about kinetic head is given to you, pressure head is given to you. So do not confuse with that, because you will think that head is not taught to us. Head, it means the energy itself. So kinetic head means kinetic energy, potential head means potential energy, and pressure head means pressure energy. Okay. So these three, this is the pressure energy, this is the potential energy, and this is the kinetic energy. Sum of these energies equals to constant. And what is this? The difference of this potential, difference of this pressure energy, difference of potential energy, difference of kinetic energy is a constant quantity. It means that energy is conserved, which means final energy equals to initial energy. Got it? So there is no loss of energy in that. This is the Bernoulli's equation, which indirectly representing the conservation of energy. And this represents the conservation of mass, equation of continuity. Now, get back to our work. Firstly, we will discuss about the Venturi meter. What is this? Okay. If you are doing, if you are able to crack the JEE mains, you will get to enter in the NIT. And then in the third semester, when you will learn fluid mechanics, there is an experiment in that to measure the flow of water. And there will be you in your lab, there is a device named Venturi meter. And with the help of that, you are going to measure the rate of flow of water. So Venturi meter is a device that we use to measure the rate of flow of water, that how fast the water is flowing, what is the velocity of the water, what is the flow rate of that liquid or fluid. Specifically, I'm saying fluid. Fluid will cover both liquid and gases. Okay. So Venturi meter, let me see. So this device is developed by Italian scientist. The name is very heavy, so I will just focus on this Venturi. Okay, and also you, I'm suggesting to you also. The Venturi is the name, and the name of that scientist, we name this device as Venturi meter. Okay. So these are the great personality in front of you. So Venturi meter is a device that measure the flow speed of the incompressible fluid through a pipe. Now, why this incompressible has been used, you will get it clear with this. So keep this term in your mind. Why the incompressible fluid? Okay. So venturimeter is clear. It is a device that we use to measure the rate of flow of water or flow speed. The rate of flow is the flow speed. Now, based on the Bernoulli's principle. Now, this is the setup of venturimeter. Are you guys able to see this? Just give me a thumbs up. Okay. So this is the setup. Now, do not confuse or do not just agitate with this. Or what is this? What is a device? You already know about this term. So Shiva is saying that pre-slide I want to present. This is the previous slide. Do you have any kind of doubt in that? Actually, I have not told anything about it now. This is a device which measures the flow speed of a incompressible fluid. Clear? And it is given by this GB Venturi. Okay. And it is based on Bernoulli's equation or Bernoulli's principle. Now, this is a setup of a Venturi meter. These ends are the broad end. You will see the area of cross section of this end is higher. And at the middle, you have a neck. It's like a neck. Our neck, this is the area of cross section is heavy here. Then we have a neck, lesser cross section area, and then the cross section area will increase. So here also, this is the base area. Here, this is the area of neck, or you will also say it the neck area. Neck area. So we have a constriction here, the narrow section, and then again the same thing. Got it? And also we have connected a YouTube manometer to it. We have already discussed about it. Okay. What is a YouTube manometer? It is used to measure the pressure difference. Huh? So this is the YouTube manometer that is connected to one of the end of YouTube manometer is connected to the neck. One of the end is connected to the here at the original cross section of the venturimeter. Now, here something in YouTube manometer we have filled a liquid of or fluid, let's say, of density rho m, and this fluid that is flowing through this is of density rho. These two fluids are intermixable. Okay, they sorry, non-mixing property they will show, because if they will mix, then how do you measure the pressure? Got it? So these are such mix with each other. Okay, and this is an upstream flow, which means they are flowing in this direction. Now, the area of cross section of this neck is A. Area of cross section of this upper section is capital A. Got it? The difference in height. The difference in height with the flow that is captured by the YouTube manometer is H. Okay. Now, applying the continuity equation between 1 and 2. What is 1? Here, from here to here, we are going to apply it. Now, A1, V1. Let's say here we have selected the area A, and the velocity here is V1. Velocity here of water is V2, because we know that as area is changing, the velocity will change. So here we have assumed the velocity to be V2. Now, AV1 is equals to AV2. V2 is equals to capital A upon A into V1. And definitely this is greater than V1. Now, if I apply the Bernoulli equation between 1 and 2, how can I apply this? We know that in Bernoulli equation, the difference of potential energy also measured, but they are at same level. This venturimeter is not tilted. Okay, this is not tilted. So this is at same level. The difference of potential energy will not come because height is same from where we are measuring it. So when we apply the Bernoulli equation, pressure at one side plus 1 by 2 rho V1 square is the kinetic energy when fluid enter in the venturimeter, plus P2 pressure at the next side, plus 1 by 2 times rho V2 square, the kinetic energy. When we can take also rho G H1, and in this side rho G H2, but H1 and H2 is same, so we can cancel it out. That is why we have not mentioned it here. Now from equation 1, we put the value of V2 in terms of V1. It is capital A by A, V1 whole square. Now P1 minus P2 is equals to rho m GH, because we know that in a YouTube manometer, if the difference in height is H, and the fluid of density M has been inside this, so the pressure difference we can say here is rho m GH. Okay, so that is why we have taken the pressure difference between 1 and 2, because end 1 is connected to this end here, and then we have a neck, and again we have this area. So end 1 is connected to this and 2 is connected to this. So here the pressure is P1, here the pressure is P2, and difference in U2 height is, let's say, it is showing H. So P1 minus P2 is nothing but rho m GH. Now plus 1 by 2 times V1 square into A by A whole square minus 1. We have taken V1 square as common and 1 by 2 rho as common. So from that we can say that V1, which is the flow of liquid at the inlet of the venturimeter, V1 is equals to square root of 2 into rho of material which is filled inside the manometer, density of liquid inside manometer, A by A whole square minus 1 raised to the power minus half. No. Okay, so this is the formula for venturimeter outflow. No, you don't need to remember this formula. Okay. You need to remember that how the concept that we have applied. We have applied the equation of continuity from section 1 and 2, and we have applied the Bernoulli equation in section 1 and 2, and then we are able to find this expression. Now divide this, derive this expression by your own self 2 to 3 times so that you will master in it. Ready for the challenge? So this is the question. The flow of blood in a large artery of an anesthetized dog is diverted through a venturi meter. The wider part of the meter has cross-sectional area equal to the artery. A is equals to 8 mm square. The narrower part has an area A is equals to 4 mm square. The pressure drop in the artery is 24 Pascal. Now, what is the speed of blood in the artery? Now, for that kind of question, you need to remember the formula. If you remember the formula, which is simple, V1 is equals to square root of 2 into rho mgh. Rho mgh is nothing but P1 minus P2. You can also remember in this way, V1 is equals to square root of 2 P1 minus P2 divided by rho, and also this is power half, so we will take it outside, capital A by small a raised to the power 2 minus 1 raised to the power minus half. This can also be taken as this. Now let's solve this question. This is the equation. V is equals to square root of 2 rho m gh divided by rho of blood A by A whole square minus 1. Now, Put the value rho m gh here. Rho blood is given to you. Okay. Then area of cross section capital A, which is 8 mm² for the bigger part, and for narrower part small a is given to us 4 mm². Got it? We put the value and got the answer, which is now rho m you do not need you here, because rho mgh can be replaced by p1 minus p2, which is delta p, and it is given as here 24 Pascal. That is why we have put directly 24 Pascal here. Based on that, velocity is 0.125 meter per second. Now, the topic is dynamic lift. Very interesting topic, and you also have observed it in daily life. You will guys will definitely connect to it. Now, dynamic lift. Dynamic lift is the normal force that we applied or that a body will feel, I will say, by a virtue of the motion through the fluid, which means we have a body. Let's say this is the body, and there are fluids are flowing on the upper surface and down surface of it, and there is a difference in the flow of that. So this body will feel a push or pull in the downward direction or upward direction by the virtue of this difference in fluid flow. Okay. Like in Shillong region, there are, let's say, a lot of heavy rain is there, and because of that, uh, high speed winds is also there. And what generally happens when the people put like steel plate, I will say, yeah, so they will have a tendency to move up when a heavy wind flow will be there. Why is so? Why is so? Why is that happening? So it is happening because of the dynamic lift. Now we will understand it in more detailed way. So firstly, the airplane wing is responsible for the providing this lift. How the airplane wing is acting? So this is the airplane wing that we have. From the side view, we are plane is standing like this, and we are seeing it from the side view. So this is the airplane wing. Let me like this. So what is happening in that? If you talk about, this is surface number 1, this is surface number 2. Got it? So because of that, the cross-sectional area or the surface area I will talk about, the surface area of surface 1 is greater than the surface area of 2. We can say that surface area of 1 is greater than surface area of 2. So if the fluid is flowing through it, fluid is flowing, and what is the fluid? Air. The air is flowing through it on the upper side and downside. So the upper side air will have to cover more distance than the lower side air. Okay. So it will take more time to cover this. So the velocity will reduce. Got it? Because it is taking more time to cover. And this side has lesser area, lesser surface area. So the wind or air traveling through this surface will take less time. Okay, and move faster. Okay, got it? So that is why if velocity is decreasing here, which means we can say that there is a difference in pressure also, because we know that the increasing in pressure, if the pressure is increased, the velocity will decrease. And if the pressure, I will write it here, if the pressure increase, the velocity will decrease. And if velocity increase, the pressure would decrease there. So because of the difference of pressure inside that, We want to move, or we want to nullify, or we want to cover that pressure difference. Okay. We want to rectify that change in pressure. Like for example, when the train came in the platform, they will say in the loudspeaker that please move away from the platform, from the yellow line in metro specifically, and in general railway station they will suggest you to move away from the platform. Why it is so? Why they say to you? Because when a train is moving very fast, so the air which is in contact with the train will move very fast. Because of that, the pressure will drop there. If pressure is decreasing, and before you, if you are standing there, this is the train which is moving in this side, you are here. So this air which is in between you and train will move with the train, along with the train, with a high speed, and because of that the velocity will decrease, sorry, velocity will increase of the air. If the velocity is increasing, the pressure will drop there between you and train. Here the pressure will drop, but before you there is no movement of air, as usual as the air is. So pressure here is greater of this pressure. So due to this, the pressure difference would be here. So this higher pressure will push you towards the lower pressure. Okay, that is why you will feel a jerk towards the train. You will, if this is you, so you will feel a jerk towards the train, and that is why they request you to move away from the platform. Okay, to be at a safer distance. So same is happening in this. This is the dynamic lift in that case also. Same is happening in this. The more time the air will take, the velocity will reduce as the time passes. So this moving very high velocity, okay, this is moving with low velocity. So there is a pressure difference and you will have a lift. Okay, now we will understand it in a more designed way. Till now, if you have any doubt, anyone, you can ask anytime. This is the aeroplane you will have, and the lift is provided by the wing here. Got it? Now, spinning of the ball is air in air is also one of the example of that. Now, how it is happening? Aerodynamic lift. This is the wing of the aeroplane or the airfoil that we have. Now, upper layer of the streamline will be like this. Are you getting this? Everyone? Okay. The lower streamline will be this. So you can see from the figure also, this would have covered more distance. More distance it would have covered. And it would have covered lesser distance. Shorter distance. Clear? This is very clear, na? Okay. So it will have higher velocity, because to cover the longer distance, we need a higher velocity in same time. So here will be low pressure. To cover this larger distance, we need an increase in velocity. Okay. And this side has low velocity because it has to cover shorter distance. Note it. So high velocity, low pressure will be there. Low velocity, high pressure will be there. So we want to move from high pressure to low pressure. So this wing will experience a dynamic lift, which also help us to lift the airplane. Got it? So the pressure on the upper surface where the flow is moving faster is lower. The pressure is lower on the upper surface, and in the pressure is lower on the upper surface and pressure is higher on the lower surface. So we want to move from high pressure to low pressure, and that is why this airfoil will experience a lift, and that lift is termed as dynamic lift. Got it? Now, see in this example, this is the example for Magnus effect. After that, we will discuss the Magnus effect. Look, what is happening in this case? Again, should we play the video once again? Yes. So let's do it once again. Sir, can we fly our bike by attaching wings both the side? Yes, you can. But for that, you need to make your bike very lighter, and the engine that is providing that power should be very high. Because in aeroplane, if you check about the material of the airplane, it is very light. Got it? And the engines that we use in that case is very high. You need to understand the concept. Aeroplane is just not only lift by this dynamic lift phenomena that is happening naturally. No, it is a supportingly providing that. Okay, it is a just a support that is provide to help the engine. The main power is coming from the engine, the turbines that we use in that. Okay. Okay. So here you will see, if you have observed it. Okay. Thank you. You got it. If you observe it, the ball is spinning, and instead of moving in a straight line, it is moving in a curved path. Why it is happening? Why? This why should be arise in your mind. Dynamic lift by the virtue of spinning is known as Magnus effect. Okay, we will understand it. So case one, when the ball is not spinning. Spinning means it is rotating on its own axis. So in case one, it is not spinning. So the velocity of air, because it is moving in the air, so air will pass through it. So the velocity of air on both the side will be same. So if the ball moves in air but does not spin, the velocity of ball above and below the ball is same. And as a result of that, there is no pressure difference because velocities are same. Got it? Now, so therefore no dynamic lift in this case. But what if the ball is spinning on its own axis? Like this. This is spinning on its own axis. Then what will happen? So when the ball will spin, let's say this is the ball and it is spinning. Got it? And you have to understand it. So when the ball spin, it drags the air above it. Therefore, the velocity above, because if it is spinning, the air above it, and it is moving in this way, in a circular way, it is moving. So the air above it, let's say, we will divide it in half and half part, and it is rotating, it spinning. So the air above it will drag this air, and the air below it, because it is moving further also, it is moving in this direction also. So this air, the upper side air will travel in this side. Got it? This air will cross in the opposite direction to the motion of ball. In the previous case, there is no difference because the ball is not spinning. So air will come, make contact and leave. But here, because of the spinning of this ball in this direction, it will try to drag the air which is passing over the surface of it in this direction. So here the velocity of the air will reduce because there is a force, or you can say the extra velocity in opposite direction. There is a drag provided by this ball. in the opposite direction to the motion of ball. Okay, got it? This surface, upper surface, is moving in this direction. Air want to travel in this direction. So this is applying a drag to this air. So the velocity of the air will decrease. But in lower side, this is moving in this direction, air also moving in this direction. So velocity of the air will increase. Got it? So if the velocity of the air increases, if the velocity of air increase here, the pressure will be lower, and here the pressure will be high. So there is a pressure difference, and the ball will also travel in the direction of pressure movement to compensate this change of pressure. Got it? And that is why it is moving away from its path. Instead of moving in a straight line, it is taking a curved line, curved path, because there is an extra force which is trying to pull this, same as of projectile motion. Because of this force, which is due to gravity, the ball we have projected here, instead of moving in this way, it is moving in this way because of this extra force, because of the force of gravity. And that is why if you take the example of ball and it is spinning, so it will move this way, not this one, because of the pressure difference. Got it? And this effect, the dynamic lift, because of the spinning of object, is termed as Magnus effect. Got it? Now, in this case, I want to discuss one thing more. Just a second. Yeah, in this case, you will hoping that might of you, some of you have this doubt. Then why the velocity of this wing, the upper side, is high, and why the velocity of this wing is lower? It is not just because of the surface area, it is because of the roughness. Because the upper surface of this wing we made very, very, let's say, it is not too rough, but the lower side is very rough. And the upper side is very shiny surface that we have, very smooth surface. So because of that, air will pass through this surface very high. Because surface is smooth, the resistance is lower, so air will move very fast. But in the bottom side, the, there is a resistance. So air try to move with the same speed, but this resistance will decrease the velocity. And that is why we have low velocity here and high velocity on the upper side. Got it? Now, we have discussed this. Any kind of doubt till now? And these are the daily life situation that we will see. Some of you have might play this basketball or cricket ball. That is why, uh, okay, one of the question that is waiting for you now, it is will be why do the bowler rub the ball? You will see generally they will rub the ball like this. Okay, why they are doing so? They are making one of the surface of the ball shiny, and the another surface that is not rubbed will be rough. So there is a difference of the roughness, and because of that, air will move faster on the shiny surface and slower on the rough surface, and they will have a Magnus effect, and that is called a swing. We will say na that the ball is in swing or out swing. So it is because of the Magnus effect. Got it? Although the bowler do not know about it. Now, this is a question. The total area of the wings of an aeroplane is 10 meters square. The speed of the air above and below the wing is 140 meters per second and 110 meter per second. Then the force on the airplane by this air is. Now, we will solve this question. This is the airplane. The upper surface is 1 and we have a velocity there 140 meter per second, and in the lower surface we have air as 110 meter. So we will apply the Bernoulli theorem. What will happen? P1 plus rho g h1 here, pressure of here, height of this point, and 1 by 2 times rho velocity of this sign, kinetic energy, plus equals to P2 pressure of this point, rho gh2 height of this point, plus 1 by 2 times rho v2 square. Now potential energy is approximately same, because this wing, what do you do about this thickness? This is very small, so we can neglect it. So potential difference is same. So here we only left with pressure difference and the velocities. So pressure difference we already know. Sorry, velocities we already know. We put the value, find the pressure difference, P1 minus P2, and this is Newton per meter square. So the force exerted by air on the aeroplane is force into, because we know pressure is nothing but force upon area. The force will be pressure into area. Pressure is P2 minus P1, which is 4800 Newton per meter square. Area, that is also given to you. So the force that a dynamic lift has applied on the airplane is 48,000 Newton. Great force is this. Now, the next application of Bernoulli's theorem is the speed of efflux. What is this efflux? Efflux means, it means outflow. So when I get a, let's say I have made a hole at the bottom of this tank or this container. So what will happen? The liquid will, or not at the bottom, I have made it somehow higher, and from the top of the height it is h, and let's say the height up to which the water has been filled is L. Okay, so I have made a hole of here which is of cross-sectional area small a, and let's say the cross-sectional area of this container base area is capital A. Okay, so here the liquid will come out like this. Now the velocity of this flow, because liquid is getting out, so this will become outflow. So velocity of this flow, this kind of flow, is termed as efflux, speed of efflux. And this phenomena, the liquid is coming out, the outflow of the liquid is termed as efflux. So we are interested in knowing the velocity of this point. Let's say it is v1. The velocity of this end, because this base area is coming down, as the liquid level decreases it will come down. So here the velocity is, let's say, v2. Got it? Now what we are going to do, applying Bernoulli equation is the Ramban in fluid mechanics. Bernoulli equation. Okay, so Bernoulli equation के लिए we have to define the point where we are applying it. This is point number 1 at this surface, and this is point number 2. This point number 2 is just outside the container. This is the container, and here we have made a hole. So this point is here. Okay. Now, applying the equation at one point, let's say the pressure there is P1 plus, here the pressure is P1 and here the pressure is P2 plus, what is the magnetic, oh sorry, what is the potential energy of this point? It is rho g L. This is the datum line from we are measuring the height. So from that, this point is of L height. So rho gl is the potential energy plus 1 by 2 times rho. V square, V here is V2, is V2 square, plus equals to, we are applying this at this point. So here the pressure is P2 plus rho G. What is the height? What is the height? It is this, not this rho GH. It is L minus H. Rho G L minus H plus 1 by 2 times rho V1 square. Now P1 minus P2 plus rho G L plus V2, if area of base is very greater than this, so from equation of continuity we can say that this area or this volume of this liquid will down very slowly. Okay, if the hole you have made is very small, so the liquid will drop to the height very slowly it will come. So we can assume that V2 is nearly zero, approximately zero, for the calculation purpose. So we have assumed it to be zero, equals to rho G L minus H plus 1 by 2 times rho V1 square. Now do it on the next page. P1 minus P2 is equals to 1 by 2 times rho V1 square plus rho G L minus H plus minus rho G L. We have take it from here to here, so minus would be there. P1 minus P2, 1 by 2 times rho V1 square plus, if you open this expression, you can take rho G as common. So rho G L minus H minus L. What it? Rho GL minus rho GH. So L and L will cancel out. So P1 minus P2 is equals to 1 by 2 times rho V1 square plus rho G, minus rho G H. Take this on this side. P1 minus P2 plus rho G H is equals to 1 by 2 times rho V1 square. Now divide this expression with rho by 2. So you will have P1 minus P2 by 2 P1 minus P2 by rho plus GH upon 2 is equals to, because if you divide this by 2, this will become, let's say, 2. It is 2GH and rho will cancel out. 2GH is equals to V1 square. So here V1 is equals to square root of P1 minus P2 divided by rho 2 times of P1 minus P2. Let me write it in a very clear way. 2 times P1 minus P2 divided by rho plus 2GH. This is the velocity of efflux. It is the velocity of efflux. Okay, got it? Any kind of doubt in this expression? Now, we know that this we have assumed outside of the container, and outside there is air. So pressure 2 is nothing but the atmospheric pressure. So we can replace it in this expression. So V1 will become 2 times P1 minus P atmospheric divided by rho plus 2GH. Now, if the container is open, now in this case, container is closed. This container is closed. Now, when we open the container, in the next case, if container is open, then what will happen? If you open the container, the pressure of this portion on portion number 1 will also be the atmospheric pressure, because only atmospheric air is applying the pressure on this side. Okay, so P1 will also result in P atmospheric, and if you put this here, P1 minus P atmospheric, and P1 is also P atmospheric, so this expression will become 0. This one. So in this case, velocity of efflux you have as root 2 gh, which is same as in a case of free fall. Got it? This is termed as the Torricelli's law. Now we will discuss it. Torricelli law. It is given by this Torricelli. So it states that the velocity of efflux for a non-viscous fluid flowing from a cylindrical tank is V is equals to root 2gh, the same that we have derived. The velocity of efflux expression we have also divided. Okay, the same thing that we have did. So here, both of the side, if you will notice, the pressure is P atmospheric. So this is known as the velocity of efflux. Okay, or efflux means outflow. I have already discussed it with you. Now, the horizontal range traveled by the liquid, this is the velocity. Horizontal range will be velocity of efflux into time. So it is root 2gh into square root of 2 into h minus h divided by g. It is same as t is equals to 2 root 2h by g, and h is nothing but the difference of height it will have take. In this case, it has h minus h. So liquid is falling from a height of h minus h. Got it? So that is why in the expression of time here, h instead of h, it will be h minus h. So remember this expression, or you don't need to remember it. If you know the velocity of efflux, then you can easily find it out. Okay. So it is R is equals to 2 h into capital H minus h. For to be maximum, so you have to differentiate it with respect to small h. So dr by dh is equals to 0. So after differentiating, we find that height for the maximum range should be half of the container height. So whenever you want to get a higher range, make a hole in the between of the in between up to the height which the liquid you have filled. Let's say you have filled the height with 10 meter. So if you want the maximum range to be there, make a small hole at 10 by 2, which means 5 meter. So that in case you will have the maximum range. Okay. So I hope you are clear with this. If you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Thank you so much for being attentive. Thank you so much. If you have any kind of doubt, you can ask. Otherwise, the lecture is being over. Thank you so much, guys. Take care. Bye-bye.